Hey friends, I'm Scott Hanselman. We're back with another Deep.net with Stephen Toub. How are you doing, sir?
I'm doing very well. How are you, Scott?
I'm living the dream, living the dream. So what else can we do? How deep can we go? I think a great place to go would be span of T, which is amazing because there's two kinds of people, in my opinion. There's those that know all about span of T and love it. And there are those who are using it and it's changing their lives every day and they don't even know it exists.
Because it's just pervasive throughout the platform.
Exactly. Yeah, it absolutely is. So one of the first hard things when you do computer science is you learn about your types and then you put them in an array. And everyone's computer science teacher or software engineering teacher had a metaphor. Mine used buckets, and they literally like lined up buckets in the row, and that's the zeroth bucket and things like that. We all have written, if we grew up in a certain generation, we wrote a mem copy. We would manually move arrays around, but maybe we should start at the beginning of why an array of things is hard or interesting.
That's a great idea. Yeah, and I love that we'll be talking about span because, as many folks who are using .NET know, it has gotten significantly faster across the board over the last decade. Huge improvements every release over release, racking up big improvements in throughput or reductions in memory consumption or startup or whatever it might be. And there are a lot of reasons for that. Sometimes it's innovation happening in the research world coming into the platform. Sometimes it's fundamental improvements in code generation or in garbage collection. Sometimes it's just sort of quantity, the massive number of open source contributions coming into the release. But there have been a few really critical turning points or revolutions almost, where some new feature comes in and just changes how we go about things day to day. And at that top of that list is span. And it really has changed what we do, how we do it, and how we think about it. So yeah, let's start with array. So to your point, let's say that I just have a simple method that uses an array. So I'm going to have a static int, we'll call it sum. And this is just taking an array and we're going to sum up the values in a very simple fashion. So I'll create a sum, I'll return the sum, and then I'm just going to for each over each value in the array and sum plus equals I, right? It's your very basic loop. And as we talked about, I think in the link part 1 or link part 2 video, this for loop will actually be lowered by the C# compiler into a really nice for loop. For I equals 0, I is less than array.length, I++, and then sum plus equals I sub 0.
Right. We're going to be trying to write performant code here. We're going to focus on performant code, but no one needs to worry about line 6. Exactly. It will be lowered. It is
the right things just happen. And we can see that the right things just happen. And I'm going to take you talked how deep can we go? I'm going to take a really, really deep dive off a cliff here. And we're going to go straight to look at the assembly code. Just because, I don't expect everyone watching to understand this particular dialect of assembly code. That's not the point. The point is we kind of get a sense for how this high level code gets translated down. And then we'll be able to see as we make changes how that impacts sort of the quality of the assembly code.
Now, when you say assembly, right now we're in idiomatic C#, then there's compiler generated C#, then there's compiler generated IL, then there's jitter or AOT assembler, which is processor specific. Are you talking about?
I'm talking about the processor specific code. So I'm running on Windows on a 64-bit, on x64 architecture. And so you would see different code if this was ARM64 or if this was Linux, the differences in the assembly language or in the calling conventions or whatever. But again, none of that really matters. We're just going to use it as sort of a starting point. So there are a variety of ways that I could get the disassembly for this function, and then pros and cons to each. One very simple one that I've alluded to in the past is I could just copy and paste this code over into sharplab.io. So if I just paste this here, I've got my sum function, and we can see that I can look at the C#. I can look at what the IL for this function looks like, and I can also ask it to produce assembly code. So this is basically taking the C#, compiling it down to IL, and then running it through the just-in-time compiler, in this case on x64 using this particular version of .NET, and generating some assembly code. So that's one way I can do it. I could also hit F5 or Control F5 and attach a debugger and look at the disassembly code in the debugger. That's another way to do it. However, there's a really handy, I can also use benchmark.net. In benchmark.net, I mentioned that there were various diagnosers. So we saw in the previous video slapping memory diagnoser on my benchmark. If I just add disassembly diagnoser, that will also tell benchmark.net to just spit out the disassembly code. Super useful, because then for a benchmark, if you're comparing before and after, you can look at a diff between the before and after and see what was going on. But there's a really interesting approach that's also super valuable, and that is we can actually ask the JIT itself to tell us what assembly code is generating. And we can do this by, let me just write a while loop here. Let me just say while true. And all I want to do is I just want to invoke this function a bunch of times in order to get the JIT to spit out what I want it to spit out. So I'm going to create an array. Doesn't matter what this is. So just do a new range 0 to 1,000.
Is this where you're warming it up? Is this the profile guided optimization where you get it to run it a couple times and it goes, oh, I finally know that that's the best, most optimized one? Exactly.
And we'll walk through exactly that part. So now I can build this. We can see it'll build and it spits out a path to my.
Okay. And there's no way we can see that unless you control scroll.
Yeah, all that was just a link to.
Gotcha. So the link to a DLL.
Yeah. So I'm going to come over here to my console. Are the fonts big enough? I think so. Yeah.
Yes, sir.
And I'm going to set an environment variable. And that environment variable will be .NET JIT disassemble. And what this is doing is telling the JIT, hey, I'd like you to actually generate and show me the assembly code. And I can then give it a pattern for what functions I want it to show me them for. So I'm going to ask it to show me the assembly code for anything that included sum in the method name. Now I just run. You noticed a whole bunch of stuff just got spewed out.
Wow.
Now I just killed it because I had an infinite loop. But if you were talking about how it can generate sort of multiple levels of, so the first time it ran here, we got what it calls is tier 0. This is sort of, I'm not going to do any optimization. Right. I'm just going to generate code as quickly as I possibly can, but I'm instrumenting it I'm sprinkling in some tracking. And the code here doesn't look particularly good. Like this is a whole lot of code for what should be a really simple thing, right?
Right. We talked about a couple of episodes ago that you can have it good, fast, or cheap, pick 2.
Right.
And this one was fast and cheap.
Exactly.
But it instrumented it so that it might get it good later.
Exactly. So then if I scroll down to the bottom, we see now we have a tier 1 compilation. There's a lot less code here. And the JIT is basically, this is the optimized version of the code with whatever learnings it had from a previous version. And we see it's a tiny little thing with 29 bytes. And there's all this other information the JIT is able to tell us because we're not just disassembling the bytes of the code in memory. This is actually the JIT showing us, its view of what it's producing. So kind of the internals of what's happening. So this is another way that I can get at that. And I use this all the time. Super useful. However, one of the developers on the JIT team, the just-in-time compiler team at Microsoft, harnessed that same output and wrote a really cool extension for Visual Studio called Disasmo, DISASMO. And if I just put my, so you can get it from extensions, manage extensions in Visual Studio. If I just put my cursor here and I do Control-Shift-D, this opens up this other window over here where it automates that process. So it built and then it loaded up.
You control scroll in there. Does it respect font sizes?
There's this little open in VS editor, which opens it in something that does. So,
I see. Cool. Oh, wow.
So I can
did all of that work for you effectively. It automated what we just did manually at the command line.
Yes, with the exception that it didn't actually run the code. It built it. And then it ran it through the JIT, but it didn't actually tier up. So you can see here on the top right, it says full ops. So this was basically disabling tiered compilation and just jumping straight to the kind of the final.
Do it right the first time and take your time and get it right.
So this is really cool. So now I can click on any function and I can just say, what is the assembly code? Control, Alt Shift D I always have to look to see what my fingers are doing because they kind of learn it and then I forget.
Yeah, your fingers know, your muscles know, but your brain doesn't know.
Exactly. So there's this very tight assembly code, and the most relevant portion of it is this part here. This is the loop. You can see it's a loop because when I click on this label, you see that there's this jump grader here that's jumping to this label. So this part is just kind of doing this, and that's that tight inner loop.
Okay. So it does the comparison on line 23, and then the result of that, it's like, okay, I did the compare. Is it greater than or less than? 24 makes the call. And if it's greater than, it jumps back and starts it all over again. Exactly.
And if you don't know assembly, not to spend a lot of time talking about AI, but one of the things that things like GPT-4 or ChatGPT or Bing Chat or Gemini or whatever your favorite thing is, they are actually really good at explaining assembly code. So, because they've seen a lot of it. So if I just highlight this code and I bring up GitHub Copilot, so I can say, ask Copilot, explain in detail what this assembly code is doing. It'll walk instruction by instruction, teaching you what each of these instructions is doing, where it's putting stuff, and 9 times out of 10, it's not only right, but it's like clairvoyant in guessing what was happening.
Wow.
And really giving you a sense for. So if you're ever looking for, like, you paste it into ChatGPT or whatever your favorite thing is, but it's a super great way of understanding the assembly.
Yeah, and I want to call something out. We've had a couple of folks in the chat, not just a little bit, but occasionally folks are saying, why is Stephen using Copilot? Are we trying to, is this an advert? This is a 90-minute long advertisement for Copilot. It is not. This is how you code. This is, you use light mode. This is your Visual Studio. This is your real computer. This is just how you work, and you discovered in doing this that it happened to be good at assembler.
Well, because I wasn't sure what was going on in one little region, and so I asked it. I was like, oh, that makes sense.
And it makes sense because there's 50, 60 years of assembler out there. That makes sense why a large language model would be good at that.
Exactly. So the key part here is there is this really tight loop where we're just incrementing incrementing the iteration variable. We're checking to see whether it's still in bounds. If it is, we're coming back. We're adding the next value into our sum, and we just keep doing that until we're done, storing it all into EAX, which in this calling convention is what's returned out of the method at the end. So that EAX here is sum. Okay, so really, really tight code for our array, and that's great. Arrays are great. But, let's say I have 1,000 numbers and I only wanted to sum 50 of them. So what do? I probably have to pass in some additional information here, like I need an offset and I need a length.
Let me ask you this. I know where you're going here. I want to make sure that we don't lose anybody who might be wondering, who may not speak assembler, but they may go, okay, I can see where the increment is in the assembler. I can see where the compare is. But where is the array? Like, can we visualize the array? Because I can see on line 1 where you just kind of without mentioning it, made an array with 1,000 ints from 0 to 1,000. But where is it? So
this array is stored on the heap. So there is an object sitting on the heap that is 1,000 integers long, plus a little bit of upfront material around how long is the array. So there's an integer that says 1,000 followed by those 1,000 integers, basically. And then I have a local on my stack. I have a local variable, which I've called array. What I call it doesn't matter, but it's just some space on the stack that's storing the address of that array. Now it's storing it in a special manner. This isn't just a pointer like you would have in C, or rather, it is a pointer, but with some special stuff, capabilities surrounding it. And that special capability is that it's tracked by a combination of the JIT and the GC. Because that array sitting on the heap, if I create a bunch of objects and some of them get freed, and then I create more objects and some of them get freed, I can end up with fragmentation, kind of gaps between these objects. And then I go to allocate something new and I don't have enough space to represent my contiguous new object because it's all these little gaps between these objects. So these these things can move. The GC can move them to defragment the heap and push them all together, which means their addresses can change. And so when that happens, the GC needs to go and update my local that's sitting on the stack with a new address inside it.
Let me tell me what you think about this analogy, because when I used to teach this, I described at the end of Indiana Jones, when they put the Ark of the Covenant back in the giant Costco in the big giant warehouse, right? It's full of boxes. It's in a giant warehouse full of boxes, and they're all the same. They're containers. But there's somebody up front with a clipboard which has a list of the location of each of the containers. And if you came in with 1,000 containers, there may not be a slot for 1,000, but I could fit 0 through 150 here. I'll write it down. I'll put it 150 through 200 over there. So the 1,000 containers get stored, but there's a couple over in the corner here, and there's a couple there, a couple up front. But I'm going to lie to you because I'm clipboard guy.
Right. Well, and then if someone comes in and does a big clearing out of all the old stuff and leaves a whole bunch of holes,
opportunity.
You can just like go to the front and just push everything together to the back, right?
And update your clipboard with
you have to update your
details.
Yeah.
Got it. Okay, that makes a lot of sense. Good deal.
So this reference here, and this will be important later as well. This reference is basically a pointer that can be updated by the garbage collector. It's a managed pointer. It's being managed by the system. Now, in terms of how that gets into this function, like what is array inside this function, we're passing some argument into this function. And that means the function needs to know where to go to get this array. And so there are things called calling conventions, which are an agreement between a caller and a callee for where the caller is going to put stuff and where the callee is going to get stuff. And by default, Windows x64, this uses a calling convention where the first argument is going to be passed in the ECX or RCX register. So if you see here, this is basically, that register is storing the address of the array. And so this check here where I'm moving something into the R8D register, this is loading whatever is stored at offset 0x8 from the pointer. It's loading whatever is at that memory location into R8D. It so happens that what lives at that memory location is the length of the array. So it's loading the length of the array into R8D. It's checking to see whether the length is 0. And if it is 0, there's nothing to do. So it's going to jump down to the end and we're done. If it's not 0, then it's going to enter our type, effectively what became a do while loop here. So that's where the array is.
Yeah. That RCX register is really interesting because it's a part of x64, but it's extending how we used to do things on x86
with ECX.
It's a backwards compatible extension, which is really interesting. And we'll get into that another day.
Yeah. So if I come back in here, let's say instead of passing in the actual array, let's say I wanted to pass in only the first 50 elements of the array that I wanted to sum. Well, I could do this weird dance where I would say copy equals new int 50 and then array.copy.
You want to address a chunk of it. You want to like say, I only care about this middle bit here.
Right. And then pass and copy. But that's a big expense if I have to create a brand new array, copy the relevant portion over. Like I don't want to do that. So
let me ask you this: go ahead and put that back. Control Z that back and make it larger. Did someone on line 5? Is there an implicit for loop in line 5, or does it address that? Is anyone hunting or searching, or do they go right to 50, but they still make a copy of it? No one's searching the array in that context.
No. So this is just doing a mem copy. This is just saying, I want to copy 50 elements from array over to copy, and then I'm going to pass that in.
Of that sub-region, which may or may not be fragmented. We don't know that. That's hidden from us.
Right. So this is in my array of numbers, I've got 1,000 numbers, but I only want to sum the first 50 of them. So I'm going to create a brand new array. I'm going to copy the first 50 numbers from the original array to my new array, and then I'm going to pass my new array in.
But I'm pointing out that the 50 could be in 50 different places, or could be 3 different places. That's all being hidden from us as well?
Well, in this case, they're all contiguous at the beginning of the array. I'm copying from array sub 0 to copy sub 0. The first 50 elements of the array and putting that into the 50 first elements of copy.
I guess I was confused thinking that, again, you what's on the heap and what's on the stack, and trying to think about if the heap has become fragmented.
Oh, I see. Well, the array itself, the 1,000 elements of the array are always contiguous. They have no space.
intrinsic types? If they were not intrinsic types, could they become fragmented?
No, they would always, well, whatever is actually stored in the array itself are always contiguous.
Okay, cool.
But if what was stored in the array was just a reference to something else, like a pointer to something else, the pointers would all be contiguous, but they could be referencing things anywhere in memory.
Okay, I'm with you now. Okay, so you grab the 50.
So I could do this, but that's really expensive. I don't want to do that. So if you see throughout kind of older APIs in .NET, you'll see things like taking an offset and a length, right? And then I could go in here and I could change what I'm doing in here. I could say, I'm going to end at some value that is, I don't need to do that. Just say for int I equals offset, I is less than offset plus length, I plus plus, and then I'm going to sum whatever is at array sub I. So I'm iterating over just a particular portion of this array. So I can do that. That'll give me the right answer. Not here, I could just pass in 0 and 50. This should be array again. But if I get the disassembly for this now, and then I'm going to ask for a diff, which I'll bring up over here. It's one of the reasons I really like this tool. You can, if we look at we focus on our loop, which is, I'm focusing on the loop because it represents the bulk of the processing. If this was 1 million elements, we're going to be doing this thing 1 million times. You can see in our loop that we now have a few additional instructions going on here. We have another branch now, another comparison happening inside the loop to make sure that the array access is still in bounds. Because this isn't that super clean pattern of 0 to array.length that the JIT can easily process. This offset and this length could be anything. I could have passed in an offset of 2,000, even though my length was only 1,000 long. So the JIT is having to do a bounds check to make sure that what I'm trying to access is still in range. And in fact, you can tell anytime there's a bounds check happening, if you go to the bottom of the method and you see this telltale pattern of calling core info help range check fail. This is a helper function that the JIT will call when a bounds check fails. And this will actually end up throwing an index out of range exception. So if this bounds check fails, you can see that it will jump down here to this cold code at the end of the method, for which it will end up throwing an exception. And I highlight this because I just wanted to get a little bit of the array. I didn't want to do the whole thing. Now I'm paying a cost for that. And it doesn't seem like I should have to do that, but I am.
Yeah, it's a significant tax.
Yeah, of per element having to do this additional branch. So that was with array and an offset in length, but there are other things that I might want to pass in here as well. So what if I wanted a list of int, right? And maybe then I also want to have lint. Maybe I also want to pass in a subset of that list offset int length.
You know, and we were taught in .NET, which, you know, for a lot of us happened later in our careers, we were taught just treat lists like an array. They're very helpful. They're so useful. Yes, there's a little bit of overhead, but we were told not to really sweat the overhead. Should we?
In general, no, you shouldn't. The overhead is minimal. If it was a super, super duper tight loop, like there's a few extra instructions. We can see that here. So if I were to just, again, disassemble this, so we're going over a list, offset and length. Like there's not a whole lot of code here, and we're still doing the whole offset.
Try to zoom in as much as you can.
Sorry.
I apologize.
Oops, wrong window.
There we go.
So, you know, again, we have a relatively tight loop here. We do notice there's a couple
compares in there.
We had the one that we saw for the offset and length. There's one more now because we're dealing with a slightly higher level of abstraction, the list on top of the array. But again, not a huge cost. The bigger cost is, well, if I actually wanted to have a single implementation that was able to deal with the contiguous memory of an array and the contiguous memory of a portion of an array and the contiguous memory of a list and the contiguous memory of a portion of this list, what do I do? Like, what is the one function that I write that allows all of those things to be expressed once. Because I could make 4 copies of this. I could have one for, list without offsets and one for list with offsets. And I could have another for if this was just back to my array. This isn't compiled because of my compile things, but just showing like all these different copies of the code to achieve kind of writing it once, being able to use it for multiple things. Now, some folks might be watching and say, well, what about interfaces? Like, isn't that what interfaces are for? And sure, I could write a single method that took an iList, and because I could even, just have it be an iList, but then the caller needs to create a new iList for the relevant subset.
Mm-hmm.
Like if I just took one that was an offset, list and offset in the length, and now I look at the disassembly for that, we can now see that this looks pretty tight, but all of the work is actually happening in this interface call. And so there's now overhead associated with this dispatch. Every time we're going back to this, we're doing this interface dispatch.
Right. You've got a tight loop and then an interface dispatch in the middle of the tight loop.
In the middle of it.
That does God knows what.
Exactly. And so, I'm fine with that cost. But now what about other kinds of inputs? What if I got what if I was doing interop and I got a pointer and a length from C or from Rust or forever, and I wanted to process, I had some zoom
in on the left side there for me.
Oh, sorry. Yeah. Or as is being suggested to me here, what if I just had a stack alloc? So if I had a pointer here and a length, and I wanted to somehow say I want to sum all of the values that are stored in this pointer up to that length, do I now need to write a whole sum function that's using unsafe code to process those pointers? It becomes this this debate between performance and maintainability. I really want the one implementation that I can give arrays and lists and stack alloc data and data that I got from Interop. I want to be able to write that once and have all the efficiency, but I don't really have a good way to do all of that and kind of have my cake and eat it too.
Why isn't it an array? Like, array feels intrinsic, like it's a bunch of stuff in a line, but I feel like we know too much, and there's hidden implementations. Like, I want something that's going to hide parts of things from me, but I also want a low level type.
Well, I could, if I had my array here, whatever I had, doesn't matter what I actually have in it. This is just data in a line. Mm-hmm. And I can, in an unsafe block, I can say, I want to get a pointer to the first element of this array.
Right. But now I'm writing C.
And now this sum function becomes int star pointer int length. And now I have to rewrite.
C# friends are like, what? And as soon as you said unsafe, you've now made a foot gun. Unsafe is your foot gun, and you're basically saying, good luck.
Unsafe is disabling what the JIT gives me in terms of things like bounds checking. When I can walk off the end of an array and the JIT says, whoa there, and throws an exception the moment I try and do that. With a pointer, have at it, have fun. Yeah. Go enjoy your AVs and your security vulnerabilities. So we try and avoid using pointers wherever we can, and we reduce the surface area that we use pointers down to a minimum. But if the only way that I could write a function that handled arrays and pointers and lists and slices is by using pointers, well, then I'm kind of forced into that world. So this is where Span comes in. Span is that thing that lets me have my cake and eat it too. If I just go back to the code that I had out here, I'm just going to go back to my regular for each loop, and I can just say I have a span of int, and I'll say for each int value in span sum plus equals value. And I can, if I look at the disassembly for this, here's my, I'm going to zoom in. I'm learning. Here's my tight inner loop. Notice no additional unnecessary branches. And yet I can call this function with my array. I can call this with a new span around my array that accesses just the first 50 elements. I can call this, if I have some pointer that I stack alloc, I can call this with new span int pointer 1000. I need to put this on the safe block for my pointer usage. Like, I can use this one implementation for arrays, for portions of arrays, for pointers, for lists if I want to. Anything that has kind of a contiguous piece of memory, I've now written my one function, and I get the nice code gen for my one function, but I can use it with all these different things.
So the span is this great unifier that acknowledges that it's more than an array, but it's an array within the context of this world we have, this .NET runtime.
Exactly. When we were talking about async and await, I think I talked about how one of the great innovation with task wasn't so much an innovation as it was just a recognition that having a single thing that you can take all of your async functions that are all doing different things, but they all generate a task. Then the only thing you need to tool is that one task. It doesn't matter that I have a million different implementations producing a task. I can write helpers in terms of task. I can write a language feature like async and await in terms of task. It's this unifier. Span is the exact same thing for contiguous memory.
In computer science, the joke about, like, what is the two things about the two hard things in computer science, or are naming things, what is it, off by one errors, and naming things. I don't remember what the third one was, but span is a freaking awesome name. When you find a name, like, I don't know if this happened if you were in the room, but there must have been a time when there were a bunch of people with a whiteboard and a thesaurus trying to figure out what to call the
right name was. Yeah.
Now, span, a concept of a span exists in linear algebra, right? It's the span of a set of vectors, but it may have been obvious. But a span for me, like, it spans, like a bridge spans space. It was a word that's not array, but expressed being more than, but also the space, the contiguous space across the bridge of something. Yeah. I just love that, because now that I get it, and it has a great name, you didn't just name it foo, it clicks for me. It spans the space.
It happens to be nice because we use it so much that it's nice that it's this relatively short, concise thing we can easily express, because this now does show up everywhere. It pervades the entire set of core libraries that make up .NET.
When we say span, we don't say span colloquially. We say span of T, span of T, span of T. Is it absolutely married to the concept of generics? Generics made span of T possible, right? Is there a span of object, or is it always span of T? It has to be a type that is specific, not just...
So there's no non-generic span. There's only span of T and read-only span of T. This could have also been
read-only span of T is a great point, actually.
And so there's basically these two ones and we'll get to kind of the core of the difference of what these are. We're going to actually implement these and we'll see what the difference is, but there's a very, very small difference between the two of them. Mainly, can I write into it or not? Yes, it's span. If not, it's read-only span.
Yeah, it's like like my floppy drive has a jumper, and I pull the jumper, and now I can't write to the disk.
Exactly. And you can see I'm passing in a span here, but there's an implicit conversion from span to read-only span. That is the pulling of that jumper, right? So now in here, if I were to try to write to span of 0, it'll say, what are you talking about? You can't do that. Even Copilot knows.
Oh, wow. That's cool.
Yeah. So span is this great unifying force, and it's allowed us to do some wonderful things. Not only has it allowed us to consolidate these places where we did have multiple copies of code paths, but it's allowed us to take code that we wouldn't have otherwise been able to express well or efficiently in managed code and do so. So for example, array.sort was implemented all throughout .NET Framework, it still is, and before .NET 5, I think, it was implemented in C or C++ in the core runtime. So you called array.sort, you would end up going into native code. And that means pointers all over the place. And that's primarily because a lot of the code where we were doing stuff, it was hitting these inefficiencies where, there'd be extra bounds checking and whatnot. And we really didn't want to afford that on this really core critical code path that needs to be really efficient of sorting. But with Span, we were able to take a large amount of this pointer-based code from C and basically lift it out, paste it in as C#, fix up a few things in terms of Span. And 99% of that code now is fully safe using Span and read-only Span. There's one little place, I think one function in the middle, where for a critical loop where the bounds, the JIT couldn't today detect that the bounds checks could be removed. We left that one piece using pointers in C#, but everything else is just Span. And then array.sort is just calling into that Span-based code. But then we also were able to, okay, now we have array.sort, we have Span sorting in terms of Span. Let's expose that, right? So now we have public APIs in terms of Span for sorting. And now anywhere you get a Span from, whether it be Interop or a list of T or on the stack or whatever, you can now use that functionality. And there are these knock-on benefits where you take it from being just in terms of arrays, now you make it in terms of spans, you maintain your efficiency, you maintain your safety, but now you can use that same functionality in all these different places. It also allows you to do some really, really, really cool things. So for example, I can write read-only span int, and I'm going to use the collection expression syntax that was introduced in C#12. So I can just have a set of numbers here. And what this is saying is I want to just construct a span with 3 numbers in it. 42, 43. I think I meant 44. Doesn't matter. 40. I can't type. 40, 44. But the really neat thing here is this isn't allocating an array. This isn't just putting this on the stack. This is actually recognizing, all right, you have some contiguous data here. You want to be able to reference it by something that you can't write to. So this data is immutable. And we could actually blit this data into the assembly itself. So just have it just live in the data portion of the assembly. And when I create a read-only span around it, I'm literally just referencing the data directly in the binary.
Okay, so hang on. Make a regular just int array with those 3, the way that we would have done in the old days. Like, no, above it. Just, int, So you've got, you're in class, it's whatever, 101, and you can make a new int. In this case here, what do we know? What does the compiler know on line 4 that it doesn't know on line 3 that can make that such a more powerful?
The compiler doesn't know whether you're going to do this.
But we hinted that we are.
This.
Yeah.
I can do that. And so this will end up being basically stack allocated space instead. But the fact that this is a read-only thing that is intrinsically known to the known to the C# compiler, known to the just-in-time compiler, it says, okay, you're never going to change this. I can just put it somewhere, where just blit it directly into the binary. And then there are things that are built on top of that. So if I said read-only byte, and I used hello Scott using the UTF-8 syntax that came in C#11. So this is a UTF-8 string, basically. The C# compiler is generating the UTF-8 bytes from this string and is blitting those directly into the assembly. And then this span is just pointing directly to that data in the binary.
Okay, this might be a dumb question, but that's the value that I'm providing in these conversations. In Unix world, there's a thing called mprotect. It's like a system call to go and say that here's some memory pages that are read-only and protected, and there you can't write to them. You can't. It's basically chmod for memory. I say chmod, chmod. Basically you're saying chmod -x. Does .NET have an idea? Like in Windows, you can say virtual protect to protect a region of committed pages to virtual address space. is there anything you can do to say that that's not only read only, but it's like protected at the operating system level to be prevented to be written to?
You can. That would be up to the runtime to do. The runtime does do things like ensuring that anywhere that JIT wrote code switches to be non-writable once it switches to being executable and things like that. But there's nothing that's exposed in managed APIs to a C# developer. You'd have to p-invoke to do things like that.
Okay, interesting. All right. So we've got a read-only span of bytes here, and it's UTF-8 bytes, and they're in the assembly. They're just hard-coded, and that's okay because it's reasonable to be hard-coded.
Yeah. And so there are these really cool things you can do. Or let me just comment this out. Take something like string. Strings in .NET are immutable objects. We really, really don't want people trying to use unsafe code to modify the contents of a string. You can do it sometimes, and it might work, but it's a really bad idea to go and mutate immutable things using pointers and stomping over data that really should be immutable. And so, for a long time, we wanted to have an API that would allow you to create a string and its beginning of its lifetime populate it with something, but then switch over to a point where, okay, now it's immutable. Now you're done writing to this. And, we contemplated exposing, imagine you had an API like create that took a delegate, say, let's say you took an action of char array or something along those lines. Then you could call this create with array, and you could write into this array to populate it with whatever data you wanted. The problem is, if we were to actually pass in that mutable string here and allow you to write to that mutable string, you could store this somewhere. You could have some static field, static char array, and then here I could say, I'm going to stash this thing away. Oops. Array equals array. And that would violate what we were trying to achieve, because now you have this mutable thing sitting out here that you could mutate later, and we don't want to let you do that. But with spans, for a reason we'll see very shortly, can't live on the heap. They can only live on the stack. And that means you can't have a static field containing a span. You can't take a span and store it away somewhere. Which means there actually is now an API on string called string.create, where I can say, let's say I want to create something that is 34 characters long. I'll create one that is ID followed by some GUID. So 2 characters for ID followed by 32 characters for a GUID. So I'll pass in the actual GUID here, and then I can say, I'm going to get a... Oh, I had these backwards. Span GUID. So now this is basically creating a string that is immutable at this point. But in here, I can write to span, which is pointing to the data for the string. So I could say something like ID as span, copy to span, and then GUID.try format into span.slice2, and I want to write as just the characters. So I could do something like this to basically get ID followed by all the hex characters of my GUID into my string, and I can be sure that no one can take this span and stash it away somewhere and later mutate my string, because there's no way to do that. You can't get this span out of this callback. And so it's allowed us to expose these APIs like that.
Where do I file that away as an application developer? Because like string.create is allocating a string that has its size determined ahead of time, right? You've got that a priori, and it's going to be one heap allocation. It's not going to do multiple allocations. And also string.create's got access to private data that we can't see. And you've hidden that in that kind of, I guess that's in that closure. So typically with, strings in .NET are immutable. So any modification is going to make a new string.
Yep.
How many allocations happened here, and what got modified and what didn't get modified?
One allocation for the string that was 34 characters long. And basically the runtime is saying, okay, strings are immutable, but as part of constructing the string containing this data, I'm going to temporarily give you access to its backing buffer to write the data directly into it, knowing that you won't be able to do so later because you can't take the span that I'm giving you and cache it away. So it's allowed us to expose additional things like that. And we are constantly discovering these new benefits that span and read-only span.
It's interesting because it's almost like I would have probably done that in I would have probably thought about unsafe, but this is like kind of unsafe, but it's probably fine. Right?
This is guaranteed by the runtime to be safe.
Yeah.
And using unsafe with pointers it's very much not. Yeah. So, yeah. So, we only have about 15 minutes left, I think. What I'd like to do, now that we've sort of talked through the benefits of span, is actually implement span. Because as it turns out, even with all the benefits that we've seen, it's incredibly simple what it is.
It's one of those things that we were like, we should have done this years ago.
Kind of, yeah. But it took a bunch of steps to get there. And so, for example, since C# 1.0, we've had ref, right? So if I have an integer, I could have some function that takes a reference to an integer.
Right, not a copy.
I can then call this and say ref I. And what I'm being passed in, as we talked about with kind of arrays and then the pointer to it, I'm passing in a pointer to this location.
Yep.
And if here I were to, if I were to console.writeLine I, and in here, if I were to set I to 42, when I run this code, and eventually my window should pop up somewhere.
Probably another monitor.
There we go.
Any monitor.
We can see that, the I out here, even though I initialized as 0, I was passing in the address. And then I set it to 42 in here because I'm writing to what was at that address, not to the address itself, not to the location itself. And I get my 42 out. So we've had this concept of ref for a long time, but this was the only place that you were able to do it kind of as part of these functions. But then over releases of C#, you started to be able to use ref in more places. Like I could also have a ref return value. And then I could say return ref I. And now this function is also able to return references. And I could have locals. I could have...
Well, hang on. When you return that ref I, isn't it all just the same I? Like you've got ref now 1, 2, 3, 4, 5, 6 times.
This is all, they're all the same one.
You're all just saying that, all those refs just to not touch that I and make sure it's the same one and avoid...
Right. They're all pointing to the same address.
Gotcha.
But the critical innovation for span was being able to have one of these, not just as an argument, not just as a return, not just as a local, but as a field. Because having it as a field basically means that I can then store it along with some other state. So imagine here, let me just Control Z back to glory. That's what we're saying, right? So let's call this reference, and imagine I also accepted a length, right? That's kind of all I need to know about a contiguous region of space. I know where something starts, and I know how long it is, and then I kind of just want to be able to pass those two pieces of state around together. Because if I can pass them around together, then my sum function knows where it's going to start, and it knows how long it's going to go. And then whatever I can get a reference to, if I can get a reference to the beginning of the data in the array, if I can get a reference to the beginning of the data in a list, if I can get a reference that is just a pointer, because I can actually treat pointers as references. In fact, we can see that. If I have some unsafe code here and I write int star pointer equals, I'm going to take the address of I, then I can also have an int I ref and say ref star pointer, and now I have a reference, a managed reference for that same pointer value. Now I can use this function with that reference and that length and do whatever I want. And so if I could just put those together as a little tuple, basically, and pass around that tuple, right? That's what span is. In fact, if we just implement our own, I can just say, I want a read-only struct. We'll call it my span of t. And I want it to have a couple pieces of information. I want that length. And then I also want it to be able to store a ref. So I'm going to say I want a private read-only ref to a t and reference. Now you notice I'm getting a little bit of a squiggle here. We don't just allow these references to be stored anywhere. We want these things to be forced to always be on the stack. So I can't put them in the heap. And that means I can't just have this be as part of a class or a struct that might be as part of a class. So we now also have the notion of a ref struct, which is just a struct that is allowed to contain references. But then that also means that now anyone consuming this, if they try and put it as part of something else, that thing itself has to be a ref struct. This is span. That is literally span. There's helpers and there's helper functions, but that's all it is.
My buddy of mine, Douglas Crockford, came up with JSON JavaScript object notation. And whenever you ask him, like, hey, did you invent this? He's like, no, I discovered it.
Yeah.
It was always there. Is this one of those kind of situations where it was always there, it just got discovered?
Pretty much. And so, we can start, there's obviously operations associated with span. So we can start adding those. But from a state perspective, if you go and look at the source.net or in .NET runtime, this is what you will see.
Seriously.
And that's it. So let's add a few things. So let's add a constructor. So I want to be able to take, let's say I want to be able to take a reference to a single item. So I'll just say reference. Oop, I didn't want my T here. Then I can just store my reference and I'll set length to 1. And now out here, I can say, let's say I had my I equals 42. And then I want a span, which is new my span of int ref I. So now I have a span that refers to the single element contiguous region of memory for I. And if I had a span indexer, which we will add in just a moment, and I came in here and said equals to 43, then if I printed out I, this would print 43. I could add another constructor that also took a length. Now, interestingly, this constructor doesn't exist on the real span because it's very unsafe. Passing in an arbitrary reference and an arbitrary length, you could, if I had up here had done 1,000, I'm passing in a reference to this I, but saying this is 1,000 integers long, I've just walked off the valid memory.
Right.
So this doesn't exist on span, but it does exist. We put unsafe stuff in places that is clearly marked as unsafe in some fashion. This exists as an API called memorymarshal.createSpan. And if you go look at the implementation for memorymarshal.createSpan, that is the implementation for memorymarshal.createSpan. So we can build those kinds of things. We could go in here and we could have another one that took an array. So I could say my span, and I want this to take an array. Well, we know the length here is the array.length, and we should probably do some argument validation, throw if null array. And then what am I going to do for reference here? Well, I kind of want to get the first element of the array, and this will work unless the array is empty, in which case this will blow up. But that's basically what it's doing. There is a dedicated API that you can call for this called memorymarshal.getArrayDataReference, which returns basically ref array sub 0. But if it's empty, it knows how to handle that. And so we can just kind of build up our span like this. So we have some constructors. Let's go add the things that actually make this useful. So I want to be able to have something that, well, I'll deal with the syntax in a second. It's going to return a t for the moment, and we're going to say this takes an int index, and I'm going to have a getter. Now I need to do a little validation. So I want to validate that this index is within the bounds. I think we talked about this last time when we were talking about link. A really easy way to both validate that index is with less than the length, but not less than 0, is to cast it to a uint so that it wraps around. Copilot knew that as well, and that's what it suggested I do. And so I could just here return then using this method unsafe.add. This is taking the reference and it's just doing pointer arithmetic. It's doing pointer plus, but in a way that's trackable by the GC. So now I have my implementation, and I could write a setter as well, or I could just make this return a ref using the ref returns that we just saw. Now I don't need a setter because I'm just returning the reference to that location that I can write into. So if I go back up here, now I can actually write what I was talking about. I can write span sub 0 equals, I don't remember what number I selected. And if I print out I get the 54 from having written through this span. And or we can build a slice routine. Slices are super valuable. Slices is just, I have my reference and my length. I'm just going to either shrink one side of it or shrink the other side of it or shrink both sides of it. So I could write, for example, I want to return a new span. I'm going to call it slice. And let's just slice from the beginning. So kind of, move the beginning up a little bit. Again, we'd want to do some validation. So we could say if the offset is greater than the length, throw an argument exception. And then we're just going to return a new span. And I'll just let it write it for me, where we're going to offset, we're going to increase our reference by the offset and then decrease our length by the offset. And now we have slice. And so out here, if I were to come in and if I were to say my span of char equals new, let me give it some char array, hello world. I say while, let me also make a little public property here. Public int length while span.length is greater than 0 and console.writeLine span sub 0 span equals span.slice sub 0. So I'm going to print out the first character, and then I'm going to create a new span that's missing that character, and then missing the next, and missing the next, and so on. And if I run this, oops. What did I do? Hold on.
Got those extra ticks there?
Yep. I did something wrong. Oh, I passed in the wrong value here.
Yeah, you can't slice 0.
I can, but it just returns itself.
Right.
So now if I look at my console over here, we can see, we're getting exactly what we expected. We're just changing the beginning offset as we go. And that's span. And now we can write read-only span. And literally like 30 seconds, I'm just going to copy and paste this.
Yeah, and you're going to set a jumper.
Yep. I'm going to do a search and replace my span, my read-only span. And now the only difference here is this needs to be read-only.
Is that serious?
That's it. Now, this saying where we have a reference to a read-only T,
yeah.
I can't write into this thing. Now, there is one other critical difference that we don't have enough time to go into, but there is an extra check that's done as part of the span constructor that doesn't have to be done as part of the read-only span constructor, and it has to do with array covariance. Or with array variance rather. So there's actually one more check here in the constructor that says if type of T is not a value type and array.getType does not equal type of this, then throw an exception. And if we want to talk more about why that is, we can talk in another video about it. But that's it. That's what these things are. And
and your point though that it needed things needed to be quietly built to make this happen. You needed you've got memory marshal, array data reference down there. You've got the ref concepts. You've got read only as a keyword. These things needed to kind of quietly exist before it could be discovered in such a clean way.
Yeah.
Once you all did that, though, how hard was it to convince everyone? And how did you all convince each other? Like, we could just start removing stuff from underneath and making .NET faster. Was there any pushback, or was everyone excited to start ripping and replacing?
Once we had it, it was a no-brainer.
Really?
And we, there were always discussions about, do we want to add X? It would allow for Y. And we still have those because, the incremental value that you get from adding something incremental, is it worth the return on, is it a return on investment or not? But at its core, it was a no-brainer, and using it was a no-brainer. Now, we had a lot of debate at the beginning about, is this exactly what we wanted? Because there are other ways that you could do similar things. For example, you could say that arrays are spans and spans are arrays. Spans aren't just a view over a portion of memory. Maybe they are the same thing, and that would have a lot of different benefits and a lot of different costs associated with it. But
Right.
Once we landed on this as the place to be, a lot of the other stuff just happened.
Yeah.
And in fact, we actually got span before we had the C# the ability to write ref. And so we built sort of special recognition in the runtime to be able to write this without actually having it. And then once we got the capability in C#, we swapped it out.
Yeah. And it was very clever. It feels like, to make span array-like, but not try to pretend that it's an array, was a smart thing, because you're making it into its own type. Everyone can live their lives and choose to write their apps and only use the things in the BCL and the base class library that they're used to using, lists and arrays and things like that. And span will just quietly do its work. But then people who are highly, highly perf focused can choose to up-level span and make it part of their lexicon, and they will be successful as well. So really everybody won when span of T came on the scene.
I think so. And it requires a video like this to kind of understand the concept and how it fits in. But once you do, when you care about it, it is invaluable.
Fan-freaking-tastic. Deep.net, digging into span of T. Thank you so much for the gift of your time. Thank you, audience, certainly for the gift of your viewership. If you like this, share it. Tell the people. And let us know in the comments what you like, what you don't like, and we'll try to keep putting together more of these. We've still got more videos to come. I know you've got a ton more in you. And soon we're going to start introducing other friends from the .NET team as well to get into deeper areas that we don't know about. Thank you so much.